My name is András Horváth. I'm from Pazmany University, and first of all, I have to tell that I've always been like curious how it would be to be in a pop boy band in the 90s, and probably this is the closest I can get with this microphone. So this is a dream come true for me. The second, which is less important, is that my background is in computer vision, but as you probably know, computer vision was devoured by machine learning. So in our lab, we're working now with speech processing, also natural language processing, and all these things. Most of the examples which I will show will come for computer vision, because these are the examples I can actually show on the big screen. But all the things I show, the methods, the methodology, and the algorithm, can be applied everywhere, because even in image processing, an image for us is basically just data. So it's a large matrix. It's about data. There's no special thing in that one. So just a few words about deep learning. Probably everybody heard about that. Everybody knows that there are many advantages and breakthroughs in really a myriad of area. Just think about self-driving cars. There are many companies working on this one. Or think about AlphaGo, which managed to beat the best player in the world, Lee Sedol, and also managed to beat 99.8% of all the other Go programs. So I have to admit, of course, there's a hype around deep learning, but if you compare it with traditional methods like decision trees or support vector machines, there are some complexity of problems where these traditional methods just really won't cut it, and this is the methodology which usually works on complex problems nowadays. And it's really important that in my presentation, I want to show you a few examples, but these are not really the cutting edge and also the bleeding edge examples which work in the lab. The examples which I will show are some which can be found in certain companies in production as well. So if you want to create a deep learning algorithm, that's great. You can solve really good and really complex problems with that. But the problem is that these algorithms has really bad generalization problems. So that's a really strong criticism. Of course, I have to admit that still they are higher in accuracy than anything else you would find currently under the sun. But a lot of data is needed for that. And I don't know how well you can see this image just right here. I try to show that if I can. So that's from ImageNet. So if you want to train a classifier on images, you can find more than 200,000 different classes. You can select any class you want. This is about like badgers, and in this data set you can find more than 2,000 images of badgers. And badgers are not something which is like really important from a research point of view, or especially probably from a financial or application point of view, but there's a lot of data. And that's not really good, because if you think about this and you want to start your own project involving modern machine learning technologies, or you want to start your own startup, or even if you work in data analytics company, the first thing that you must have is a large amount of data. And it's really difficult to gather a larger amount of data, because all these methods and 98% of modern machine learning techniques are in the part of supervised learning, which means that you need annotated data. And in the era of big data, it's not a really big problem to gather data, but to gather input and desired output pairs, it's really it's a humdrum and a tedious job to annotate all the data, get a huge annotation team. And if you start a project, you will end up realizing that most of the money will not go to algorithm development or machine learning experts, or just providing power to the GPUs. Most of the project resources will be needed to annotate the data, for example, by hand. And that's not really a good thing. And the other thing is that you can collect data, and the worst question that I usually get at projects is that, okay, but how much data do I need? It's not about the sheer amount of the data, but it's about the generality of the data. You really need general data which really represents for the distribution of your problem, what you want to solve. So if you just gather data, for example, for a self-driving car in good weather, well, you can get like 100,000, 10 million, 100 million data points, that car will probably not work in a rainy weather condition or in different domains. So it's not about how many data points you have, it's about how good your data is. And statistically, most people try to solve this problem by just gathering more and more data, and by this we try to make sure that our data will be better by this. But also it's about like how balanced the data set is. So for example, let's imagine you want to build an algorithm for credit card fraud detection. And if you gather like a million samples and you end up with just finding one or two fraudulent credit card usages in that data set, then that's not really a general data set. It's not really good for your problem. So what could you do in this one? And generally, if you gather a lot of data, well, your algorithm will work. If you've ever worked with computer vision, you probably have seen this is the MNIST data set. And if you use a classifier on this one, you will see a really nice distribution of your data points. And that's good. And that's how deep learning works if you have a lot of data. Could you do this if you would have like 10 samples or 100 samples? Well, not really. And if any company would ever tell you that they can do this by just with a reduced amount of data, by using 10 samples or 100 samples, well, it's either a huge scam or they use some sort of black magic, or I don't know how they do that, but in both ways, you should really avoid that company. But then what could we do and what could help us? The only thing that could help us that humans can really easily solve this task. So even if I reduce this data sample and I show this to someone who've never seen that many samples, and to use machine learning in this one, where you have only like 100 samples from these digits, no algorithm will work on this one. But if you give this to a human, it will definitely work. And I can prove this to you. So for example, these are, I don't know how well you can see that, but these are the Chinese symbols for numbers. And if I would give you 10 minutes to learn this one, you will be able to learn this definitely. I'm pretty sure. There will be no test, so you don't have to do that, but you could do that. And it's about like adaptation to the data to different domains. So for example, because if you see this really nicely written number 2, let's say, with the Chinese symbol, you will be able to apply it in real-life samples, where there's larger variation in the data. There will be different cases in that one. But so domain adaptation is a really big deal that we're really good in this one. And domain adaptation is a method which can be used to reduce really the data which is, or the real data which is needed for training this algorithm. So for example, let's think about it that tomorrow our plan is to start a new company in just building self-driving cars. So what's the most important thing for that? The most important thing would be a really good data set. How could we generate a really good data set? Well, we can have a large team and they will put cameras on their cars and go around in the cities, and we can hope that they will see a few accidents, they will see different weathers, different cases, but this is just statistically ensure that I will cover all the possible cases. Wouldn't it be better if I could like simulate all these elements? And I can create a simulation. This is from a quite famous game engine, probably you know GTA 5. And the good thing is that if I have a simulated environment, I can control what kind of data samples I will have. And I will also have the labeled ground truth of this one, just from the simulation, because the data is built up like that way. So on the left, you can see the original input image, and on the right, you can see like what would be the ground truth for semantic instance segmentation. And you don't need a large team who would annotate you this data. So that's a good thing, and you can use this for all kinds of algorithms, not just for segmentation, but for optical flow, which would tell you like in which direction and in which distance the objects are moving. Because this is a real three-dimensional environment which you build basically. You know everything there, and it's really easy to generate the ground truth data. And it's really cheap. It's much cheaper. Like in a weekend, you can generate 10,000 samples to train your algorithm, and you can tell whether they should be in a sunny environment or a rainy environment, and you will have all the ground truth labels you want to use. You don't need an annotation team to do that. And that's great, but of course you can tell, and you will be right, that the simulated data will never, ever be identical to the real samples. It will be different. It will be slightly different. So Yeah, and that's a problem. And what happens usually? Well, our algorithms will not be that good, but that's where domain adaptation will help us. So let's assume we have this case study or problem where we have a few real-life samples. So we gather that. Let's imagine I just put my camera on my car, went around in the streets, but I don't really want to annotate that data because it's expensive, it's a tedious job, and so we will just leave it that. But I have real images, and this is our target domain. So I can tell that, okay, we have some real images. And on the other hand, I can have a slightly similar data from a simulator where I can control what kind of data I need. I can control the number of samples. I can make sure that this is general. There are foggy weathers in this one. There's hail, sunny images, all kinds of cars in this one, which I have. And this is just directly annotated because I know everything from the simulation. And this will be our source domain. So could we use somehow the information in the source data to exploit it and use it on our target domain? Well, let's just try this. So what will happen with a good neural network? With a neural network, usually we will have a feature extractor layer. So these are usually like convolutional kernels, which will try to find certain patterns in my data. Here I will have an embedded representation, a feature vector describing what's there. And the whole method is basically trained. And in the end, I have a classifier. And if I train this on the simulated data, this works really well. So that's OK. I can reach really high accuracy on this one on the simulated data set. What will happen if I try this on real-life images? Well, we can try that out, and we don't really know. But if you really just go and make this test, well, in the end, you will realize that you have to submerge into complete agony and total despair because it will not work in real life because your two data sets are just different. So then what was I talking about? So you have this source domain and you have your target domain, and if they are different, then they put them together. You have something like this, which you cannot really classify. But could you somehow ensure that you transfer the domains into some sense when they are easily classifiable? And that's where domain adversarial neural networks are for, and it's a really nice idea. The only thing is that we will have your original classifier, so it's there. And here, I will just add another extra end to this one, another neural network, which is another classifier. But this will not classify what the object is, but it would classify whether my original object came from the real domain or the simulated domain. So let's see how this works in details. So in step one, I can train a classifier on the source domain, and I train my network on that one. The source domain was the simulation. So it works well, I train it, and this network will tell me whether there was a car on the image or not a car. Okay, but I cannot really use this on real data. So after that, once I have this, I will go to step two, and I will iterate my classification on the simulated domain where I have labels. Plus, what I can do is I will simultaneously show real samples and simulated samples to my network. And I will not use this end of the network, but this one. And this classifier should tell whether my image came from the source domain or is one of the simulated images or one of the target images. And here I can reverse the gradient of this network. And so I will train this network that the aim of this green part is to fool this classifier. So I want to find a feature representation of the elements here in the middle where none of the classifiers are trained could tell whether an image came from the real domain or the simulated domain. What will be the result of this one? It will be that this embedded feature will be the same for both domains. So if something is developed on the simulated domain, it will work on the real-life domain as well. And this is a really nice trick which you could use in this one, and even if your original classifier didn't work, you can make it work on real-life data. And I could show you numbers and these things. I know you're technical people, like how many percentages you can improve in your data. But I will just show some images, which is called like Cicada, which is a cyclic domain adaptation network. So this is a cycle-consistent domain adaptation. And what you can do here is that these are some images from GTA 5. Unfortunately, they are not that nice from there. And there's a real-life data set called cityscapes for self-driving cars. And what you can do is that here you have an image, you can show what the domain adapted image would look like, and you end up something like this. And you can go the other way around, where here you would had a real-life image, and you can tell how this real-life image would look like in GTA. So you can bring the two domains together, and you can also do, this is a still nicer result. It will be just published on CVPR in 2 weeks. So image generation from segmented domain, where conditionally you can have a parametered segmentation map when you can tell that, okay, here there should be some road. Okay, sorry, the displays are really dark, so you cannot really see that right now. Well, you can see this. Here the blue would be some cars, this would be some trees, and what you see there is, and really trust me, are really photorealistic generated images, which you cannot tell from real life images, and you cannot tell whether these are different or not. So this is a good thing to gather data from simulation, and with this, you can basically control the distribution of your data, so you can create samples. Like, for example, you don't have to wait for an accident to happen. You can create a simulated environment when an accident will happen, and overnight you can generate like thousands of cases of this one. And in your classifier, these data points will be exactly the same as it would came from real-life data. So this is one thing which could help you reducing the data hunger of machine learning algorithms. Of course, there's like no magic tricks, so there's no free lunch in this one. You cannot decrease the number of data points, but you can really generate the data points instead of trying to go out into the wild and gather the data and annotate the data. So whatever application you will try to just solve in the future, it always makes sense that, what do I know about the domain? Could I just generate something which is really similar to my real life data, and then maybe instead of gathering 10,000, 100,000 or 10 billion samples, I can generate something which is similar. That goes also for language processing or speech recognition and so on. The other thing that I would like to show is that another criticism towards deep learning and current machine learning techniques, that there are certain cases which we humans can easily solve, like zero-shot learning and one-shot learning, and these methods without any modifications are really bad in this one. So humans can solve problems without like a vast amount of previously annotated data points. There's like a say in English that fool me once, shame on you, fool me twice, shame on me. So this would generally mean that I should learn from 2 samples, right? Because then it's my problem if I've seen something like twice and I cannot learn from that. So we're good in this one, and I will try to demonstrate this. Okay, so this will be a test. It's no Chinese characters, but I don't know who knows what a quokka is. If nobody knows, that's really good, okay? So a quokka, the Latin name of the quokka is Cetonis brachyurus, and this is just here to show you that it's not about the sheer amount of data. This data is true. That's the Latin name of the quokka in the taxonomy of Linné, but this has no value for you, right? So you still don't know what a quokka is. But if I show you 4 images, and this is zero-shot learning, could you tell which one is a quokka? Number 1, 2, 3, or 4? So let's just vote because, well, democracy is a cool thing. So who thinks that 1 is the quokka? Nobody. Okay, that's cool. Who thinks that number 2 is the quokka? A lot of people. Okay, that's good. You're really smart. After this, I will still ask who thinks that number 3 or maybe number 4 is a quokka. So everybody knows that, right? You have never seen a quokka before, but you can still identify it. And of course, you were right, that's a quokka. And we can easily solve this task, which machine learning algorithms wouldn't be able to do. And basically why? Because this depends heavily, of course, on the classes that I was showing here. But still, no algorithm could solve this. But it also depends heavily on your prior knowledge of what kind of classes and what kind of animals you have seen before. And you identify that that's a giraffe, that's a moose, that's a golden retriever. So this must be a quokka. And that works, and this is something we never really see in neural networks. If you want to do a classifier, let's say you have a dog and cat classifier. Here you have like 2 neurons. One is like firing for dogs, the other is firing for cats. You train this for a problem. You want to solve another problem and maybe add another class, like you want to identify quokkas or want to identify, let's say, giraffes with this one as well. Then you have to retrain your network. You can learn do transfer learning and similar things, but that won't really work. You have to change your network architecture, add a new neuron here, which will represent your class, and do the whole thing from scratch. We always do the whole things from scratch, and with neural networks, you never build up on like previous knowledge. And it's because the classes are tied to the architecture. So if you use like a normal convolutional neural network, that will limit how many classes there are. And that's not how we will do that. If I would add like a 5th or 6th class to the previous task, which you already know, the problem would be the same for you. And then there's another test. This will be the last. So this is one-shot learning. You have seen one quokka image in your life now. So could you tell which one is a quokka? This is more tricky. But I don't know. So let's say this is number, sorry, there are no numbers. So this is number 1, this is 2, this is 3, and number 4. So who thinks number 1 is a quokka? Nobody. Okay. Who thinks number 2? Okay, there was 1 vote for number 1, 1 vote for number 2. Number 3, who thinks it's number 3? Okay. And who thinks it's number 4? Well, the majority, so it's democracy, so I don't dare to tell anything else. Number 4 is the right answer, of course. And you could still do it from just one example. But how do you do that? Well, so there are 2 different types of learning. Well, humans can also synthesize rules and patterns and like have really abstract and high-level information from data. This is what currently goes in convolutional neural networks, classification, and deep learning. We get a lot of data, and you get out which is really specific and characteristic for the whole set. From many examples, we do that. Like, for example, if I know that, do you know what a vehicle is? You have a really abstract representation. And in a vehicle, there are cars, tricycles, motorbikes, trams, but you know what that is. But in case of one-shot learning, and in case of a limited number of examples, you will not really do that. You will not identify like what a quokka is, but you will try to do like a pattern matching to the previous image. Not like pixel by pixel, but in a weird and strange feature space. But that's why we really see like complex similarities between like certain images, where we tend to see like faces in many different regions, and between like strange object, we see certain features where you can tell that, yeah, these images are like really similar. So we'll try more like matching these images. And there's a really cool idea called matching networks, which can really help in this one, and can really help in that not to do everything from scratch and not to just throw out everything on the window which you did before and do your training earlier. And the main idea will be basically the following. Let's say we have a neural network which is called like G theta here. And this neural network is used not for classification, but to create an embedded representation of our data. So here we use this neural network, one data goes in and it will be embedded into this vector. And then there will be another element and another and another, and these are called supports for my problem. And I will have an embedded representation here, and I will have an input element, which is usually called a query element, which I'm interested in. Like, okay, this is what I'm really interested in. And this will also go to the same network. And I will try to find the similarity between these elements, between these embedded representations. The similarity can be in any metric space, for example, in cosine similarity. And it's a really good thing that here it's a similarity. And it's a metric space because here I can tell things that this belongs to none of the classes, which you cannot really do with like normal convolutional neural network. Or you can tell that this belongs to both of the classes. And you can have things like this. And I will have my expected output during training, and I will train my system, like showing an example. I know that this should be an output of red, so this vector should be the closest to this vector, and could be as far as it's possible from these 3 vectors because they belong to a different class. So instead of classification, this will create an embedded representation of these embedded features, where they will be like really separated in space. They will be put like into different positions. And the good thing is that here, the architecture is not tied to the number of classes. I can train this with just these 2 classes, and then my input would either be blue or yellow, just the 2 doc types. Here I can put like 100 different classes, and I can change the classes just freely as I want. I can add like a 5th class here, a 5th support with a green label, and then there will be also possible outputs in the network for that. So that's a pretty good thing, and this could be really used in practice. Like for example, in matching networks, the good thing is that we use a metric space. This is usually for high dimensional vectors, is cosine similarity, and I can pre-train it on different classes on different data, which might be like irrelevant for my actual problem, but could contain information for that. For example, let's just think about this example that I want to build a classifier for letter recognition. Okay, so here are my letters, they are handwritten, and the problem is that I'm a lazy guy and I only have just one sample of each letter. So just one letter A, one letter C, and these things. And if you try to do deep learning on that one, it will fail miserably. You cannot do that. But what you can do is that let's assume that what kind of other data sets could I gather, and this is good in every project if you use this network architecture, which is in some way relevant for my data. So instead of like using these characters, I can find a lot of other ABCs and other letters from the Hebrew alphabet, from Bengali, from the Cyrillic, from Lord of the Rings, from Futurama, and a lot of different symbols. And what I can do with this, that here I can train my network just on these samples, not on the samples which is really relevant for my problem. And sometimes I will here just put like one letter from the Futurama ABC and one from Bengali. And then my query element would be the same from, let's say, Futurama. And then those two elements should be close together, and the other two should be really far. And then I can put like two other supports, one from Hebrew and one from Sanskrit, and like that. And sometimes I can put there 3 supports or 4 supports or as many as I want. And in the end, I will end up a generic like letter recognition system, which will not concentrate on these classes. It will not concentrate on Bengali or Futurama or these things, but all of them together. It will be able to identify like which letter was used there. And what can I do with just the one samples which I had? Once my network is trained on this data set, I can put my support elements here, the real supports which are relevant for the problem, A, B, C, D, and these ones. And my query element can go here, because on this data set, the network will learn that there are like horizontal lines which are really important. There are vertical lines, there are endpoint and joins for these lines, and it will learn some generic information. And I don't have to throw this out. I can just change the classes, change the elements here, and use the same network with the same knowledge which was synthesized on this one, which could be generic, on this data set, and test it on my original data and my original problem, and it really helps a lot. So the other thing that you could think if you just came across to any machine learning problem, that is there like any other data sets which would be like relevant, even just slightly relevant for my field, and then you can go to these architectures and not just train on your data, but your application specific data, but train on some data which is which contains some information which you could really use. So that was just all, and I just want to show you an independent test set of quokkas. Probably you can identify all of them, and so thank you for your attention.